Good morning, everybody. My name is Steve Miller, and I'm responsible for storage architecture within the data center group at Intel. I'm going to talk a little bit today about rack scale design and what we chose and why we chose SPDK to do our ephemeral and non-durable storage and kind of how we led up to that. And I want to, before we start, acknowledge a couple of folks that contributed greatly to this, Sid and Sujoy, who have been some of the primary architects on this. So what I'm going to go through today is going to do a brief overview of RSD. As a show of hands, how many people know what RSD is? Okay, good. Well, then this will be some new information. I'm glad some of the Intel people raised their hands. That was good to see. I'm going to talk a little bit about the storage feature requirements that we were trying to accomplish and what we kind of looked at there. And then I'll talk a little bit about why SPDK really fit for, and this doesn't have a great name, high performance persistent storage pool. If somebody come up with a better acronym, I'd love that. We've went through about 3 or 4 of these. But fundamentally, what we're trying to do is be able to disaggregate SSDs and then reattach them in composed fashion. And you'll see what we're trying to do and why this worked very well for us. And then I've got a little bit of performance data. It's a little bit older version of SPDK, and we're doing a little bit more than what you're seeing upstairs in the, I think, 8 or 9 million IOPs per core. But still, it's really impressive performance when you compare it to almost anything else that does this kind of capability. So to start a little bit about, what was the motivation for RSD? It's been a project that's been ongoing for over 5 years at Intel. Today the data centers are growing at a phenomenal rate, and people aren't building data centers the same way they built them 30 years ago or 20 years ago, where they were very stovepiped with very fixed workloads, right? Today's workloads are very dynamic, and what you're running this morning may be what you're not, completely different what you run tomorrow. Or even in the afternoon, and those different applications are going to require a different mix of computational power, of storage, of maybe accelerators moved in. So you'd like to be able to quickly tear down and recompose systems to meet your workloads. That's going to be the most optimal way to do it. And RackScale was built around that concept of being able to disaggregate various components. In this particular case, we really talk about the storage components and the accelerator components, and then be able to compose back up virtual systems that are optimized to run that workload. And the initial release, when it first came out, used PCI as a fabric to do that composition, that disaggregation and composition. And as we move forward, we've been moving into supporting that with Ethernet. The current release, I believe it was just released this week, is RSD 2.4, and that does have NVMe over fabrics, which is really what we're going to talk about today, the disaggregation point. So it was built on standards. One of the real challenges is if you put something together and you're the only one building it, it really does make it less desirable for people because they can't innovate in that area, and they don't have interoperability, which is really important. So you can see that the RackScale design as an organization has most of the big players in it, Dell EMC, Ericsson, Huawei, Inspur, just to name a few. So there's a lot of people building RSD compliant gear and building solutions out of it. And you can see here when I talk about how you take a disaggregated rack of compute, storage, and accelerators, and you compose with the set of software APIs through Pod Manager, compose nodes that match what you need. So you can see that it's really important when you want to compose these things that you address both bandwidth and latency so that you make these devices look like they're locally attached to the server, right? They perform similarly to locally attached. You don't want them to perform a lot different because if they look a lot different, then they're not going to deliver the same performance and people are going to want to go back to the stovepipe kind of model. So the benefits, as I talked a little bit about before, resource pooling. So one of the real challenges you see with these next generation SSDs is you get hundreds and hundreds of thousands of IOPs. We're probably just short of getting to 1 million IOPs in a single SSD, and as soon as we get to Gen 4, we'll probably start seeing million IOP SSDs. That's very hard for a single server to consume. Also, we see incredible size SSDs, 16 and 32 terabyte, and they'll continue to get bigger. So obviously, putting one of those devices in a single server and having that server consume that device is probably going to be not always the most efficient way to do it. So being able to disaggregate them and serving up a piece of that. Also, in doing that, you may have different applications. Some applications are more interested in the capacity of an SSD. Some may be more interested in the performance of an SSD, but not as interested in the capacity. By slicing that SSD up and giving a small piece of it to an application that wants high IOPs or high performance, and then leaving the rest of the capacity to go to something that wants less, may be the most efficient way to using that SSD rather than stranding resources. But in order to do that, of course, you have to have an interconnect that provides the latency and the bandwidth in order to do it. So that's kind of on the resource pooling. The other piece, modular refresh. As you have this disaggregated resource, you can change your mix. So if you have fixed-based things, and this is particularly true in, say, like a hyper-converged kind of thing where you're adding servers with a fixed amount of compute and storage and maybe accelerators, then every time I want more storage, I have to add more compute or accelerators or the like. When you have a more modular design, you can say, well, I need another petabyte of storage. I'm just going to roll in storage resources and connect it in. I have enough compute. Or vice versa, I have plenty of storage. I need more compute. So I roll in more servers and connect it up and be able to serve it up that way. So you get a more modular refresh. And of course, all of that drives your data center efficiency. So drives your operational costs down.
What kind of network interconnect do you recommend for connecting the compute and storage nodes?
Okay, oh, you're a great lead. I think it's the next slide. One more slide, and I'll get to that. But it's the short answer is Ethernet, but I'm going to get to it. Again, here, I talked a little bit about this. This is more exactly how this works. The resources are pooled. Part of the BMC allows to compose the system, and it gives you your composed nodes through the orchestration software, the pod manager that RSD has. The original system that we did, rack scale, used PCI as its fabric to disaggregate the various resources. The challenge with PCI, it's very low latency, very high bandwidth fabric, but it does have a somewhat limited radix and is somewhat fragile from a fabric standpoint. So it doesn't really, you can't really build very big PCI infrastructures. Ethernet, on the other hand, is an extremely robust 40-year-old technology that has grown with the industry and really is the fabric of choice. And I think there's many in the industry that says, well, Ethernet always wins. And certainly in the last 40 years, that's kind of been the case. So as we looked forward in wanting to get to the newer versions of RSD, both 2.3 and 2.4 have NVMe over Fabric added in. And it's really, I'm going to talk about why we went with SPDK when we decided to go with NVMe over Fabrics on Ethernet. So here's kind of the model that we've kind of adopted as part of RSD with disaggregated storage servers feeding compute servers. Now, we could have gone a couple of different paths, and we looked at several different ways to disaggregate NVMe SSDs over Ethernet and be able to build composable systems. There's certainly a number of devices out there today, both in ASIC or FPGA form, called bridges that do the NVMe conversion to NVMe over Fabric. They're very low latency, they're very high performance, they're fairly limited in feature set. And so we looked at those and decided that what we really wanted to do is something that had a little bit more capability to it. We wanted for storage to drive some of the features in there. So clearly we wanted performance, we wanted low latency. That was a given, we couldn't give up on that. But we wanted to put a set of features in that would enable things beyond what you could do with kind of, the more simple-based bridge devices. So one of the things we wanted to be able to do is create logical volumes that had performance greater than a single SSD. Because as you look today, SSDs are not quite at the same speed networking is, right? Networking is going up in leaps and bounds with 100 gig and 200 gig. So we wanted to be able to do kind of a RAID 0, a striped performance to get logical volumes with greater than a single SSD performance. We wanted to be able to do some of the more basic storage features of things like clones and snapshots, and of course thin provisioning, which is huge in trying to drive efficiency in the data center. We wanted to be able to put in the hooks for quality of service, because when you build pools and try to drive multiple different applications from a single target, quality of service is important both at the target and of course at some point quality of service in the network is going to be important too, depending on how big you build that and how hard you want to drive the network. The other thing that was important to us, the efficiency of the use of resources. So the processor and memory, how efficient we're using that. If you look, there are storage solutions out there today that are pretty heavyweight, that use a tremendous amount of CPU and memory resources to do a fairly modest amount of IOPs. And the flip side is the stuff that SPDK folks are showing today, where I think 8 million IOPs per core, I think is the new number. Now, we'll show a little bit more modest number because we're doing a few more things. We're doing the clones and the thin provisions and all that. But still, we would not be able to do it with a kernel-based system that starts off at 1/10 the speed. And of course, standard-based management is really important to us, and simplicity of use. So that was kind of the feature set. We said, okay, how are we going to do this? And we started looking around, and we looked at both Linux kernel type stuff. We looked at reinventing the wheel, because all engineers start off by saying, I know how to do it better. And then we spent a lot of time with the SPDK team and really kind of got into what they were doing and said, wow, you've done like 80% of the work. We didn't tell them that, but yeah, they had about 80% of the work done. And we said, wow, for just a little bit of work, we could get all the things we wanted. So that's kind of where we went in developing this high-performance persistent storage pool. So what did we actually end up with? Well, we ended up with an all-flash NVMe target that delivers very high IOPs and very high throughput, and I'll show you some performance data on that. We optimized our target stack with pooling our NVMe SSDs, and we did a kind of a smart volume management, right? We wanted to be able to make sure that we're getting the most out of the media that we have, both NAND devices and Optane devices. We wanted to automate things, so we have a kind of a policy-driven storage composition that combines not only telemetry from the devices, but leverages a bunch of features that are in the Intel SSD. We wanted to support very large-scale installations. So, on a single node, we support up to 8,000 volumes. Today, we've tested up to 2,000 and have that running in the lab. We wanted to be able to do thin provision and snapshot capable volumes. Thin provisioning is something that's done quite a bit. When you think about VMs and you think about, I'm going to not have my local SSD on my server, and I'm going to pull some number of logical volumes and give them to the different virtual machines that are running on a server. Although you may say, well, here's a gigabyte, or here's 500 gigabytes of storage. The odds that they use all of that is pretty low. So being able to thin provision back means that I can have a lot less storage capability, but present a lot more to the user. And if I create that pool large enough, then the numbers actually work out, right? Thin provisioning within a single server is kind of tough because I may have 4 or 6 VMs, maybe 10 VMs at most. But if I thin provision across a rack where I have 20 or 30 servers, now all of a sudden we're talking about hundreds of VMs, and the law of large numbers helps you there.
Are these slides going to be available?
That's a good question. Nate, are these slides going to be available?
Yeah, this is being recorded.
Okay,
Yeah,
awesome.
Posted once.
Checking with the legal counsel here. Thank you. And of course, like I said, we just released RSD 2.4, so a lot of this data is in there. Not everything, but a lot of it's in there. So again, kind of to recap some of the key features that I kind of went through, we decided to go with very high speed NVMe over Fabric, RDMA accelerated. So we currently are using Rocky. We are in the middle of standing up our next generation NIC, Columbiaville, which does both Rocky and iWarp. So we're looking at both of those as well as doing NVMe over Fabrics over TCP. Now that's going to use substantially more CPU than the hardware accelerated ones, but it does give you some niceties in that it's riding on top of 40 years worth of TCP development and the kind of whole flow control that goes there. We use Pod Manager to get our volume management, and we leverage the thin provisioning snapshots and clones that come with SPDK. We do data at rest security and multi-tenant volume level security. So you're kind of getting those features that you might get from far more expensive and complicated storage systems. As I said before, we're working on a quality of service, both rate limiting and guaranteed bandwidth at the target. That's the first step in providing end-to-end quality of service, which is something that we're looking at how do we do going forward. Centralized storage manager, the pod level, so pod manager. We're doing a bunch of proactive stuff with, understanding the life of drives, making sure that we can predict ahead of time when things are going to fail. So one of the real advantages is if you know something's going to go bad or possibly is going to go bad in the next week or month, you can actually take steps so that it doesn't fail while it's working. And that's a big advantage, a big time saver to people because you don't have disruptions, right? And so we're really working on trying to understand that. I can't say enough about the scale and performance of what we've done. We've clearly been able to run up to 400 gig. Now that's 4 strands of 100. And we've cooked in up to 8,000 volumes per storage server. And again, I think we've tested about 2,000. All of the management interfaces, Redfish and Swordfish compliant, so they're industry standard. There's nothing special here. In fact, we've worked with a number of partners who are building NVMe over Fabric products of their own that we've worked together on. Well, we're going to support these interface. Others have decided to look at that. I think I've talked a little bit about the telemetry. So if I look at kind of the block diagram, what were some of the features that I thought were really good to help drive good behavior it's not as much fun as Paul, who has fun for his developers, but wanted to have an environment where people would code in a more optimal way. And one of the niceties is SPDK gives you that developer environment where kind of good behavior is driven, and I'll talk a little bit more of that in the next slide. It's a user space app, which is always much better to develop and debug in. Kernel-based things are tougher to develop in. And you don't have, of course, system call overhead. And then, without having to deal with interrupts, you can dedicate resources to drive things. And that's, if you think about, 20, 30 years ago when we first came out with real-time OSs, that's really what they were. They would assign cores to it. So this is, in some sense, what's old is new again, the capability of assigning cores and having them do fixed functions is the way to make things fast. So some of the more innovative coding techniques, right? Driving lockless architectures or near lockless architectures, that's very important in order to get performance, right? And encouraging people to not do locks. Having a good infrastructure for intercore messaging is important, especially if you have to do a lock. I mean, if I think about 10, 15, 20 years ago, storage is one of the first embarrassingly parallel programming things to go do. And what was the first thing we did? We'd put a big lock around the whole thing and say, okay, we're gonna do an operation, we're gonna lock everything. And really that's kind of the almost worst thing you can do, and that's why a lot of storage systems don't have the performance they could have, because they weren't really designed to be lockless, and SPDK enables that. Core affinity, there's a number of things that come with core affinity. Probably most notable is you're not thrashing the cache. So if you're not thrashing the cache, you're gonna get better performance, because the difference in latency into first or second level cache compared to either going to the last level cache or going out to DRAM is several orders of magnitude in some cases. So really keeping things on that core is going to give you the best execution performance. And SPDK really helps you do that. And of course, then error handling, being able to push error handling onto the right core that needs to be able to address that. So on the scale and performance, as I talked before, I think we can show that the SPDK is about 8 to 10 times faster than the second best alternative, which is the kernel, and they're actually showing that upstairs. As I talk about here, we're easily getting 8 to 10 million IOPs. Now, we're getting that upstairs on one core. In the environment we're doing a few more cores than that, but we've added extra features in, right? We've added all of the RAID 0 and the clones and the other features that are in there. As we look forward and we go from 100 microsecond media to 10 microsecond media, it gets more and more and more important how the overhead of that storage software stack is. If you look at more traditional storage stacks, you may see the time to do an IOP measured in hundreds and hundreds of microseconds to small numbers of milliseconds to do an IOP. Here we're talking about things that are in tens of microseconds or less to do an IOP, the software path, which is important. Take advantage of the new faster media. Clearly today we have up to 8K volumes. We can do in a single volume up to 128 terabytes. We can do a couple petabytes in a single storage server. That's kind of the limits we have today. Going beyond that's fairly straightforward. It's really just building something that's much bigger than 2 petabytes and testing it where we're at. So I'm going to jump a little bit into performance now and show you some performance. There are some kind of unique data pieces here. We still continue to work on this. The storage server that we're using is a pretty heavy-duty server. It's got 36 cores. For most of these charts, we used 100 gig Mellanox card and 8 P4500 SSDs. So they're somewhat older SSDs. Most of the cores are sitting idle. In this case, we use a couple of cores on each socket. You can see the Fedora Core 26.
Hey, Steve. Hey, if you wouldn't mind maybe just kind of reading some of the things that you have stacked there, because I think it's hard for some folks to see back here.
Sure. I actually have to get close to this block diagram to read it. So, on the top, we have our NVMe over target, NVMe Fabric target, and we're kind of showing a couple of subsystems, and it goes into the BDEV subsystem. And I'm sure that some of the guys here are probably much more fluent in this. But we have a couple of paths in, right? We can come straight into the BDEV and go right to the NVMe BDEV module. That's kind of what they're showing for the fastest possible performance. We have a pooled volume BDEV module, and that's how we get that slicing and striping between that and the logical store. And so you can go in and add different BDEV modules to increase functionality and features. And that's really what we're doing. We're adding different features in here, different modules that provide those features in this framework. So you maintain the fastest possible data path. And of course, down here we have the NVMe PCI driver and the SSDs below it. On a separate note, I will share a story on this. We'd got this system up and running. We were doing SSD testing, And I had a summer intern working in the group. And I asked her, I said, well, you know, I wonder if we could use the same infrastructure and serve up hard drives, right? Because you figure, well, hard drives are so slow that the network latency is not even going to be noticed. And literally in an afternoon, she replaced this driver down here with the SATA driver from Linux kernel. And by that evening, she was serving up basically HDDs over NVMe over Fabric. And we actually tied it into bottom end of SAF. And we're running storage disaggregated on NVMe over Fabric. So, you know, the key takeaway was that this is so modular and so standard interface that we could just pop it in, and it just worked, right? You know, usually you think about, I'm going to change completely different protocol. Would take days, weeks, you know, maybe even months to get something like that working. And we were able to drive that.
I see that the storage that has Mellanox connectix adapters, so that means using Rocky instead of...
So the, okay, oh yeah. So the question was, we're showing a Mellanox ConnectX 5. I'm suggesting Rocky over iWarp. So for the purposes of this performance test, which we ran probably about 3 or 4 months ago, we ran it with Mellanox chip because that was really the only 100 gig network that we could get. Our Columbiavilles were not, which is our 100 gig Rocky iWarp NIC, was not yet available. So we are redoing all of these tests with Columbiaville, and we're actually looking at Rocky and iWarp. I think both the accelerated RDMAs protocols, Rocky and iWarp, have unique characteristics. And in certain situations, I think we'll find one or the other is better. We're going to try to highlight what those are and try to give some guidance on, you know, if you're looking for this kind of performance or that kind of performance, you know, you might want to look at one versus the other, right? As an example, iWarp, you really only have to retry the one packet that you lose. Where Rocky, I believe currently you have to retry everything from the lost packet back. Now, I think they're trying to address that, but I think the current state of Rocky, certainly in these adapters, that's the way it works. So there is still some work going on in that area.
I have a question similar to this. Have you already tested with NVMe or TCP and used, for example, offload TCP on the NICs?
So the question is, have we already tested with NVMe over TCP and tested it with offloads on the NICs? So we've done some testing there. It's not complete. It is certainly some of the that is one of the project pieces we're doing along with the Rocky and iWarp with Columbiaville. And we're looking at not only the TSO and RSO and the typical hardware offloads, but there are some other, and I think it's called ADPQ, something like that, that's in Columbiaville as well, that we're looking at to see what benefits that's going to do. You know, I was very interested to hear the user space TCP/IP stack that people are looking at in SPDK. That might be something that, you know, can we move that into an SPDK and get some acceleration? So I think there's a lot of fertile area there to go mine, because there is sets of customers that would prefer to stay in TCP only and not go hardware accelerated. That will come at some cost in terms of compute power, and we're trying to figure out, you know, where's the right place to put that. You know, perhaps smart NICs might be a way to do it in the future as well.
One more question related. Most of the performance is on bandwidth and IOPs. How do you, or anything handling on the consistent latency?
So that's really important, you know. So understanding the tails is really important, and there's really two, maybe three components for tail latencies, right? There's software tail latency, there's media tail latency, and then there's the entire infrastructure, which could be caused from failures and stuff. You know, I'll talk about the first two. There's not a tremendous amount we're doing directly in this program to deal with media latencies today. Now, obviously, we're trying to be proactive in understanding the wear on an SSD. And of course, as an SSD gets older, that's when, of course, its tail latencies increase. So we'll have the ability to detect and understand it. That'll bring those tail latencies down. The fact that SPDK is lockless and user space really means you don't suffer from the kind of wide variety of interrupts going at particular SPL levels and suspending your thread, right? You have your core and you're running on your core. So you can get much more deterministic if you code correctly in SPDK than you could, say, if you're coding in the kernel. So, if you code poorly, of course, all bets are off, but you have the tools to make things much more predictable in this case. Okay, I'm going to jump to the couple slides now. I will point out this is pretty much 100 gig Ethernet limited in the read case. That's, you see 3.14 million IOPs. You multiply that by 4K, you're going to get pretty much line rate. For the writes, we're pretty much limited by, again, what the SSDs are going to be able to take in this particular case. When we're streaming, so the 128K block size is effectively streaming. We're at line rate for the 100 gig, and you can see our Q depth 1 is actually quite good there. That's kind of the kind of best case. I'll show you a couple of charts here. I know this is going to be really, really hard to see in the back. But the yellow and the blue, the yellow is the volume with one SSD in it, the yellow, and the blue is the single SSD. So basically what this shows is that our pooled volume overhead is near zero, right? You pretty much can't see the difference. So as we create pooled volumes out of more and more SSDs, again, the overhead's pretty small. Right, you just really don't see it, which allows us to do these pooled volumes and deliver higher IOPs and higher bandwidth and be able to slice and stripe them, right? I mean, I think one of the exciting things that we can do here, and I referenced this earlier, is you can take a set of SSDs and you can create stripes that might be instant stores for people who want some local high performance and serve it up directly to that compute server, set of compute servers, and you can take, again, those same SSDs and carve up a slice that is a whole bunch of capacity and say, give it to, a Ceph OSD and say, here's your volumetric store, right, your capacity store, and we'll cap your amount of I/O because we know the OSD can't go to it anyway, and that is how you'll leverage your capacity. Just a couple more here. Throughput scales as the pool goes wider, and of course the Q depth is at the initiator. You can again see that everything kind of scales up really nicely until we hit the network saturation. There's some interesting anomalies that kind of occur at the end we're kind of digging into. But again, you can see here our single drive and our pooled is basically the same. That speaks to the efficiency of the code that's in there. And again, here's a little bit more on the read IOPs. Read latency, obviously as you bring more drives to bear, and the depth goes up. Let's see, and this is the one where we're still trying to understand beyond this point here. There's some weird queuing events that are happening, we think. We haven't quite sorted that out. But with that, I'll entertain any questions.
Hold on, let's use the mic, if you don't mind.
Sure. Hi, Steve, thanks. So I'm a little bit confused as to the what HPSD is. Is it a reference architecture? In the context of this meeting here, where we're looking at PMDK and SPDK, we're talking about libraries. Really didn't see discussion of libraries here, so I'm trying to understand what this is. What is there? Is this a product? Is it a design experiment? What is it?
Yeah, that's a really good question. I wish I could give you a super good answer. I mean, first of all, part of what I'm really want to talk about is what can be done with SPDK, right? So we took this tool suite and we built a very high performance instance store. Now, exactly how we're going to productize this, whether we're going to make this, I mean, a lot of the pieces are in the 2.4 RSD spec today, both code and the documents. Some of the things I talked about that are still in development, like the quality of service, is not there. So I can't really comment on when they're going to hit because we don't have a real schedule for that. But I can say that a lot of the fundamental pieces that we use are in SPDK, and you can very quickly put something together to match this. You know, if there's strong interest and it's something that you really want to have, we can certainly talk about, you know, can we get you the bits ahead of any particular release. So in some sense, this is more of a proof of concept of what can be done. If we decide to turn this into a product, that's something that's, you know, certainly being discussed. You don't get to ask a question. I get to ask questions. I didn't ask any when you were
Ask
done.
anything I want. What's your favorite color? So you mentioned QoS. Are you guys leveraging any of the QoS features in the BDEV layer?
That's a good question. I think we are, but I can't absolutely tell you for sure. You know, we do have our first QoS operating, but I don't know. I don't know if Sujoy did the QoS.
Okay.
So I don't know if he did it. Yeah. Can you know the answer to this one? Oh, great.
Yeah, so you guys do have a more customized QoS. It's different from the one that we have in the BDEV layer. So the one that we have in the SPDK BDEV layer provides some basic QoS metrics, but I think the one that you guys are using, it's far more elaborate and sophisticated and custom.
I knew it was kind of complicated because Sujoy did it. Had a lot of features in it, but I wasn't sure if it leveraged your tools or not.
I'm just looking at the architecture. I'm assuming the compute servers are used for computation like database and things, whatever they're doing. Mm-hmm. My question is, SPDK is actually amazing that they've provided this great application level, at least with the performance. What happens when I put the SPDK in the storage NIC itself, or let's call it the NIC with the storage, and put the SPDK there, and then leave the CPUs to do pretty much nothing? The storage service is basically in the NIC itself. Because the CPUs in a blue field and things like that already have a lot of CPU. So an SPDK gives me to put that there.
So I think there's a couple of pieces, right? I always split it up into there's an initiator and a target, independent of where you put them, right? You have an initiator and a target. So you can say, I'm going to take a smart NIC, you know, that has enough CPU and enough memory bandwidth and enough I/O connectivity, and I can make that smart NIC both my initiator and my target, right? You could imagine doing that, right? And on every server, I put some SSDs, and I can serve them remote, and I can, you know, access them locally, and I can do all of that. You could also say, well, I'm going to take the smart NIC, and I'm going to make my smart NIC my target. And maybe my smart NIC is an initiator, but I can also make my smart NIC a target. Well, really, if you think about it, a smart NIC is an SoC, right? It's, you know, it's an integrated processor, memory, and NIC. And those have been around for a long time. So the then question becomes, how big a pool do you want to have, right? So a typical smart NIC maybe supports 4 to 8 SSDs, and maybe has a couple memory channels. And so if I'm looking for a fairly lightweight target, then a smart NIC I think works really well. If you're trying to make the pool fairly large, right, say I want to maybe do 16 SSDs, now do I need to add switches? Does that make it more complicated to my smart NIC? Am I better off picking an SoC with integrated networking capabilities, right? And there's you know, we and others have a number of those types of things. Or do you want to have more flexibility and be able to do choose your own network, right, independent of it. So I think it really depends on, you can certainly do that, and I think SPDK enables all those. And really depending on what your needs are, I think there's a solution out there that fits.
I'm going to add a little bit to that if I might.
Sure, please
And
do.
I think some of it just depends on your use case too, right? So when you look at where smart NICs fit, they're typically most often for infrastructure offload, i.e. I want to, Amazon Nitro, type of thing where, hey, I want to use my cores. I want to sell my cores to people that are paying for them, right? I want to sell my big cores. So where am I going to run my storage stack? Well, okay, I'll run it out on a smart NIC, right? So in that situation, right, it makes a ton of sense to have your NIC doing that because those cores cost money, right? That's what you're selling, So I think you have to really look at that.
Answer this question of yours. Ultimately, you're limited with the bandwidth anyway because coming in is 100 gigabits. So whatever you're doing is coming in at 100 gigabits.
Right.
So the question is, there are now many cores, and the PCIe switch fabric is inside those SoCs now.
Yes.
So your channels have increased greatly.
Right.
With Bluefield.
Again, it depends how many SSDs do I want to put on that smart NIC, right? If I want a bigger pool,
But it's limited by the bandwidth anyway. So 100 gig is what you can get. It doesn't matter how much your NVMEs you have on the right side. Your
so
100 gig is what
bandwidth
it is.
bandwidth is a metric.
Right.
It's not the only metric for some people, right? So again, as Nate points out, depends on the use case. Oh, you got it? You can play Vanna?
So something that's missing here is volume reliability, data reliability. You talk about performance in RAID 0, but there's kind of a dearth of focus on, erasure code or RAID 1, something that's kind of SSD specific as far as that reliability model. Is there?
So next year's talk might be more interesting for you. Yeah, I guess that. I mean, so I'll give you a teaser.
That
As-
wasn't a teaser? That
Pardon?
sounded like a teaser to me.
As you disaggregate and create pools, the pools can get fairly large. And the larger the pool gets, the more efficient you are at thin provisioning. But the larger the blast radius, effectively, right? So if you don't do something to raise the availability, then you have a situation where if I have a couple SSDs on a server and they go south, I lose 4, 6, 8, maybe 10 VMs. If I have a set of storage servers in the bottom of a rack and I have 30 servers in a rack, I don't lose 20 VMs. I lose 500 or 1,000 VMs. Now, of course, that becomes noticeable to customers. So I think there is definitely a push as we disaggregate and drive efficiency and resources that driving availability is going to be important, but maintaining performance at the same time. So a number of the things you pointed out are all ways to raise availability, right? And so again, what's old is new again. But that is something that we need to do, but we need to do that in light of making them appear to be locally attached devices, which is really the challenge. How do you get the performance out? And that's where I think SPDK is going to play a huge role.
Any other questions?
Could I ask a second one? Can I ask a second one? It was like slide 4 or 5. You had, I can't remember, you had 3 columns, composability in the middle, management on the right. You didn't spend any time talking about management. It looked like third-party management or something like that. I was trying to understand that.
So we have, Rackscale has our pod manager. And we could go on quite a bit on that. I didn't want to turn this into a pod manager talk. So it's standard-based, redfish, swordfish, and you can choose your manager of choice, right? But the important thing is all the infrastructure uses a common set of interfaces. So if you have your specific GUI tool of choice, you don't have to use ours. You can, as long as it supports the standard interfaces.
Out of curiosity, do you have some slides which show overhead of enabling snapshots on writes, for example? Overhead of snapshots?
Are you asking, are we doing copy on write snapshots or?
Yeah.
So since we have a layer of metadata, we don't have to do the traditional, we can write in other places. Now our block size is a little bit bigger than 4K, so there is some copy, but it's not, the traditional way of, I'm gonna copy the whole volume, right? It's just that little piece. And that's a basic SPDK function. That's, we just leveraged it.
I think this is probably the last one. I think.
Yeah,
we're
they're
about
getting
out of time.
tougher, so.
As my understanding, once SPDK crashed, any BDEVs and the database and data path on top of it will disappear. Any recommendation that we can recover from SPDK crash to recover BDEVs and database?
I think that's actually a Jim question. It's the recovering the database in the BDEV layer after crash.
Yeah, so I mean, if you look at the diagram that Steve had up, so all the stuff for the logical volumes, how that pool is sliced, that is all stored on metadata. So what happens in that case is when the system comes back up, the pod manager, the management software is going to reconstruct that pool with the NVMe SSDs. You'll be able to get all the metadata off of them, and then you'll be able to get those BDEVs back again. You'll have to attach them again. You'll have to relaunch the, whatever the storage services is in the VM, but you'll be able to still have that data. But yeah, until it gets relaunched, that data would be unavailable, of course.
Right, and of course, anything in flight
Yeah.
at the time is going to get lost, which is, again, as we talked about earlier, being able to recover or maintain your availability is going to become more and more an issue as the size of the pool gets bigger.
Okay, I think that's it. We're out of time.
Okay.
Thanks, Steve.